Hello and welcome to lecture 46 of the course Computational Complexity. In the previous lecture, we saw isolation lemma, which gave us a way to assign weights to elements of a set in such a way that there is a unique minimum weight set in some family. Right? So consider any family of subsets of that, and whatever be the family, isolation lemma tells us that if you assign weights in a certain uniformly and randomly from a range, there is a good probability of finding a unique minimum weight set in the family, right? So in this lecture we will see how to use isolation lemma to output a perfect matching of a bipartite graph in parallel. Okay, so as I said before, there are lots of other serial algorithms for computing the perfect matching and outputting them, but this is a parallel algorithm. This algorithm is by Mulmule, Vazirani and Vazirani, right, who also discovered the isolation lemma as part of their paper. Okay. So some of the elements of this proof we already saw in the previous week. So given the adjacency matrix, we saw we could make the TUT matrix, but in this proof we will not make the TUT matrix, we will use a different matrix. Okay. So we start with the TUT matrix, okay, or the adjacency matrix, right? Suppose this is the one that I have circled here in green is the TUT matrix. What we do is consider the elements x11, x15, etc. as some elements of a set. Now, corresponding to x11, we will introduce a weight w11. Corresponding to x15, we will introduce a weight w15, and so on. Where each of these weights, so each of these entries x11, x12, etc. are entries corresponding to certain edges, right? Zeros correspond to non-edges. So corresponding to each of these weights, we pick random values. Okay, so I'll denote them w subscript e, and we pick them from the range 1, 2, 3 up to 2 times the size of e. Okay, so there are 100 edges in the graph. We go up to the range 200, 1, 2, 3 up to 200. So twice the number of edges. Okay, and then what we do is we pick random weights like this, and then you assign in the matrix B, you assign 2 power that weight. Okay, so not just that weight, we need to assign 2 power that weight. So 2 power w11 will correspond to the edge e11. 2 power w15 will correspond to the edge between 1 and 5, and so on. And this gives us the matrix B. Okay. As we saw in the last lecture, if the matrix B is non-zero, that means there is a perfect matching. But there is some possibility that there is a perfect matching, but still somehow terms of some terms cancel, so that the determinant of the matrix, I think I misspoke before. If the determinant of the matrix is 0, if the determinant of the matrix is non-zero, then there is a perfect matching. But it could somehow so happen that there is a perfect matching, but still the determinant could become 0 because of some terms cancelling each other, right? And what we hope to achieve or accomplish using isolation lemma is that the weights will be assigned in such a way that if there is a perfect matching, then the chances of cancellation are very, very low, and that will be assured using isolation lemma. Okay, so what we do is we compute the determinant. So this is first we describe the algorithm, and then I will explain why this algorithm makes sense or why this algorithm works. So compute the determinant of this matrix B. Okay, this is the same matrix above, one with the 2 power etc. If the determinant is 0, then you output there is no perfect matching. Okay, so this algorithm can still have errors. So there could be a perfect matching and we still could output 0, but we can limit the error, or we can even compute the probability of error. Okay, so we'll see when that happens. If determinant is non-zero, then we know for sure that there is a perfect matching. Now the goal is not to decide whether there is a perfect matching or not. The goal is to output the perfect matching, right? So let's see how we do that. Now compute the determinant. So of course we already compute the determinant. Now you check the largest number r such that 2 power r is a factor of determinant b. Okay, so compute the largest number r such that 2 power r divides determinant of b. Okay, so this till this point it is done serially. Now what we will do is the rest will be in parallel. Okay, so rest can be done separately by one processor per edge of the graph. Okay, now what can be done is for each edge in the graph, consider. So what you do is you, let's say you consider this edge, for instance, edge 5 1. Okay, so now you replace edge 5 1 with 0. Okay, so this edge, this entry instead of 2 power w51 will become 0, and this, so for the edge e we call be as the matrix obtained by setting that entry to 0. Okay, now you compute the determinant of be. If the determinant of be is 0, you output e. So what we will do is we will do many parallel outputs. Okay, so this branch will only output e or not output e. Okay, or it will say no matching at all. In fact, no matching will already have been said in the earlier part. Okay, so if the determinant of b is non-zero, then it outputs e. Sorry, if the determinant of be is 0, it outputs e. Else what we do is you compute, again we do the same thing, we compute the largest re. Okay, so this looks kind of like an L, such that 2 power re divides determinant of be. Okay, so I'll just replacing the e's to actually look like e's. Now it looks, sometimes it looks more like L than e. So compute the largest re such that 2 power re is a factor of determinant be. Okay, now so recall we earlier computed this r, which was the biggest. So it was where b was this original matrix that we have here, and be is the matrix corresponding to where each edge entry or the one edge entry is replaced by 0. And then we again computed, or earlier we computed r such that 2 power r is the largest factor of b. Okay, or the largest r such that 2 power r is a factor of b. Now compute the largest re such that 2 power re is a factor of be. Now compare r and re, right? And if r is strictly smaller than re, then you output e. So there are two cases where you output e. One is when the determinant of be is 0, or when the r is a strictly smaller number than re. Okay, so notice that from in step 4, from where I started step 4, I am just focusing on one specific edge, and this will be done in parallel by different processors, for independent processors for each edge. And the claim is that each processor at the corresponding edge will correctly output E, even only if E is part of the perfect matching. Okay, so which perfect matching? There could be multiple perfect matchings, right? So here is where isolation lemma helps. Maybe I'll just write here, I'll just write a bit here to explain. So what is happening here is that if G has a perfect matching, right, then there is then only then the rest of it makes sense. But now each matching can be thought of as a subset of edges, right? Each matching is a subset of edges, and you can compute the weight for them. and the weight of each matching can be computed. So the base set here has size of E many elements. It's a base set. In the case of isolation lemma, it was x. It was the size of x was n, small n. Here the size of E is well, it is just the size of E, and the range here is going up to 2E. Okay, so by isolation lemma, probability of a unique, maybe I'll just write it in the next line. There is a unique min weight perfect matching is at least 1 minus size of E, which is the number of elements in the size edge, divided by 2 times E, which is simply half. So with probability half, there is a unique min weight perfect matching. So that is, with probability half, there is a unique min weight perfect matching, and if there is such a min weight, in that case the algorithm above will correctly output that unique perfect matching. So what the algorithm will do, we'll see the proof now. The algorithm will output this unique min weight perfect matching. So let's see how that happens. Okay, so if the isolation lemma works as in, if there is a unique min weight perfect matching, this algorithm will correctly output the unique min weight perfect matching, that matching. If it does not work, meaning if it does not have a unique min weight perfect matching, then there is no guarantee. So in this particular assignment, the probability of that happening is half, but this need not, you could choose the weights from a bigger range. Instead of 2E, you could choose it from 10E or something. So the probability will be, instead of half, it will be 9 by 10 in that case. Okay, so you can improve the probability of doing that. Okay, so now the rest of it, please assume that there is a unique min weight perfect matching, and then we will see how it outputs the same matching. Okay, so consider this matrix here. This is the same matrix B, and consider the circled edges here. Right, there are 5 circled edges, and these form a perfect matching. Now this contributes to the determinant. Right, this is one permutation. Right, and the contribution, the term that is contributed to the determinant by this perfect matching is 2 power W15 multiplied by 2 power W22 multiplied by 2 power W33 multiplied by 2 power W44 multiplied by 2 power W15, or sorry, 51. This could be plus or minus depending on whether this permutation is a odd or even permutation. So the contribution is this highlighted quantity, 2 plus or minus 2 power W15 multiplied by 2 power W22. So the product of these 2 power something can be written as 2 power, you can add up the exponents, right? So it is 2 power W15 plus W22 and so on. So instead of multiplying the 2 powers, you could just 2 power, you could write it as 2 power the summation. And so basically it is, what is the summation, what is the exponent here? The exponent is nothing but the weight of the matching, right? So a matching M, right, contributes a weight plus or minus 2 power the weight of the matching, right? That is the contribution to the determinant, right? So the determinant is just a collection of such matches, or the collection of such sums. So just to elaborate a bit further, so what I am saying is the determinant is summation of matchings M plus or minus, so depending on the sign of the matching or sign of the permutation corresponding to the matching, 2 power weight of M. This is what the determinant is. Okay, where weight of M is just the sum of the weight of the edges. And this is something I already said. By isolation lemma and step 1, with probability at least half, there is a unique min weight perfect matching. Okay, just to see it, you can consider F as the collection of all the perfect matchings. Now let W be the weight of the min weight perfect matching. Okay, W, capital W. In that case, if you look at this sum over here, if you look at this sum that I have circled over here, it is a collection of things. It's a summation of 2 power weight of some things. 2 power, now W, capital W is the smallest weight, right? That means for all the other matchings M prime, okay, so let W be the matching M, and for all the other matchings M prime, the weight of M prime is strictly greater than W. Right. So again, we are in this case where there is a unique min weight perfect matching. So all the other matchings M prime, the weight of W, the weight of M prime is strictly greater than W. So that means all the other matchings contribute at least 2 power W plus 1. They could be 2 power W plus 2 or 2 power W plus 3 or 2 power W plus 100 or something, right? But at least 2 power W plus 1. So the determinant of B, okay, so there could be plus minus of all this. So there will be one 2 power W term, right, and the rest all will be, at least you should be able to take out. So what I am saying here is the determinant, right, will be one 2 power W term plus the rest of it all will be multiple of 2 power W plus 1 and some factor. It could be a positive, negative, something. Which means you could take out the 2 power W and then say 1 plus 2 times the factor, which is exactly what I have written here. So determinant of B is, you can take out the 2 power W and then 1 plus 2B, that B is the same thing as this factor, and B will be an integer. It could be negative, it could be positive. This means, so this 1 plus 2B is an odd number, which means 2 power W is the largest power of 2 that divides determinant of B. Right. And here if you look at the algorithm, we computed the largest R, that's such that 2 power R is a factor of determinant B. So this B, this W that we computed, or the R that we computed, is actually the weight of the min weight perfect matching, unique min weight perfect matching. Okay, so till now it's clean. Now let us see how the magic happens in the parallel steps. Okay, so the parallel steps, we are supposed to each edge does something on its own, or the processor corresponding to each edge does something on its own, and automatically that is supposed to output that edge if and only if that edge is in the unique min weight perfect matching. Okay, so now in the parallel operations, we remove each edge, right? We remove each edge and compute the minimum weight perfect matching. Okay. Suppose E is not in the min weight perfect matching. So for instance, in this matrix, in this matrix over here, for instance, this edge W21, the edge 21 is not in the perfect matching. So if you remove 21, the old unique min weight perfect matching still persists, right? So W will be the unique min weight perfect matching's weight, right? And then still, if you look extracted the largest factor or largest power W for which W2 power W is a factor, you will still get the same thing, right? So if E is not in the min weight perfect matching, so again this looks like L, so I will write E, then RE will be equal to R, right? Because the unique min weight perfect matching is retained. if E is in the unique mean weight perfect matching, okay, then that unique mean weight perfect matching is now losing an edge, right? So in this summation over here, right, now this 2 power w will go, because that one edge that is part of this 2 power w is now being removed. So this will now become 2 power w plus 1 into the factor, right? So because of this, if E is in the unique mean weight perfect matching, the term corresponding to this vanishes. So determinant of BE will be actually be 2 power r into 2b. So which is what I have written here, 2 power w plus 1, or 2 power r into 2b, or maybe 2 power w into 2b. I have already said that r and w are the same. So the RE will be at least r plus 1, right? Another possibility is that if you remove E, there is no edge, there is no matching at all, in which case determinant of B is 0. In both these cases, when RE is greater than R or when determinant of B is 0, the algorithm, determinant of B is equal to 0 here and RE is greater than R over in the step D. In both the cases, E is output, right? So in both these cases, we output E. And this is exactly the cases when E is part of the unique mean weight perfect matching. RE greater than R when there is E is part of the unique mean weight perfect matching, and there are other matchings, other perfect matchings. And determinant of B is 0 when the edge E is part of all the perfect matching. So if you remove E, then the graph does not have a perfect matching, right? So if we get an instance, so what this is saying is that this correctly outputs the edge E if and only if it is part of the unique mean weight perfect matching. If it is not part of the unique mean weight perfect matching, it will not be output, because it will basically this 2 power w term will still remain, because it may be part of no other matching, or it may be part of some other matching which is not the unique mean weight perfect matching. So that will not change the 2 power w quantity here. So it will not change anything else, it will not be output. So if we get an instance, if isolation lemma, the randomness is such that we get an instance where there is a unique minimum weight perfect matching, right? In that case, this algorithm correctly outputs this perfect matching in parallel. Okay, I will just erase this all. So this algorithm is correct. And notice that from here on, right, this step 4 is entirely parallel. Each processor is only looking at that corresponding to a particular edge E. It removes that edge, basically it computes, it removes that entry from the matrix, it makes it 0, and then computes the determinant, and then computes the largest power of 2 which divides the determinant, and then compares with whatever was already computed, whatever R was already computed, right? So that's all that it has to do, and then magically this leads to the correct answer. So there is a probability of error, but that probability of error is universal, meaning if the isolation lemma doesn't work, right? If we get with half probability, we are supposed to get a unique mean weight perfect matching. If we don't get that, then it will not output the correct answer. But if we get that, it will output the correct answer. And if you are not happy with the probability, we could increase the range. Instead of 2 times E, we could choose let's say 10 times E or something, right? So this will give us a better probability of success. Anyway, so this shows that this shows how we can compute or output a perfect matching in a bipartite graph if it has one in the randomized NC. So all that you do is you replace, you get random weights for each of the edges. You replace the terms of the adjacency matrix with 2 power the random weights, and then you compute the determinant of this matrix, call it B. If determinant is 0, then there is no perfect matching. If the determinant is non-zero, you compute the largest R such that 2 power R divides determinant of B. Notice that if there is a unique mean weight perfect matching, the determinant of B will necessarily be non-zero because we already saw that if there is a unique mean weight perfect matching, the determinant of B will be 2 power W into an odd number. So it cannot be 0. This odd number is an odd number, right? So it cannot, this means that if there is a unique mean weight perfect matching, it cannot cancel and determinant of B cannot be 0, right? And then you compute the largest R, and then you do it for each edge in parallel. You remove the entry corresponding to that edge and then compute the determinant. You call it BE, determinant of BE. Then for each BE you compute the RE, the largest RE for which or such that 2 power RE divides BE, determinant of BE. And then if either RE is strictly greater than R, or if determinant of B is 0, then you output E. And this works whenever the isolation lemma has worked. If there is a unique mean weight perfect matching, this algorithm correctly outputs in parallel each edge that is in the perfect matching. So each processor that corresponds to each edge will either output the edge or not output the edge. And the point is that if there is a unique mean weight perfect matching, the correct matching will be output by the individual processors. And this shows that we can output a perfect matching in a bipartite graph in RNC. And with that, we will conclude this lecture 46. So in lecture 45 and 46 together, we showed that the decision, or not the decision, the search version of outputting a perfect matching is in randomized sensing.